Charlie Stillwell is a hydrologist at USGS. He studies urban hydrology, stormwater management, and hydrologic alteration. He specializes in data science and employs various statistical modeling and machine learning approaches. And on his USGS.gov staff profile, he has a whole list of projects he's been involved with. So, much further ado, Dr. Charlie Stillwell.
All right. Thanks, everyone, for being here and for the introduction. Greg talked all about how SELDM works, so I'm really just going to dive into a specific application of SELDM that we've worked on in North Carolina with the North Carolina DOT to basically build a decision support tool to help them with their kind of preliminary planning of a new highway project. So I think this is common terminology across all states, but I don't work in DOTs, so maximum extent practicable for stormwater treatment. Does everyone know what that means? I see mostly nodding heads. Yeah. So okay. So maximum extent practicable is basically we want to treat the stormwater as much as we can, but to an extent that it is still practicable. What that means in practice, though, is a bit fuzzy. Is practicable designed in terms of maximizing the treatment of the water, or is it in terms of the cost to the supplier? There's a lot of ways to define that. It's kind of fuzzy. In North Carolina, at least from what I understand, the determination of MEP is case by case for every project, decided with discussions between the regulators at the Department of Environmental Quality and the hydraulic engineers who are working on that project. So it's good because there's not a prescribed solution that's a cure-all for every project, but it sometimes can be a little bit inefficient. You got to start with a clean slate on every project, and there's also some subjectivity as well. Depends on who that regulator is for a project, the experiences of that hydraulic engineer. The determination of that MEP, can be a bit subjective, basically. So we worked with the North Carolina DOT to try to reduce that subjectivity and provide a data-driven solution that helps us determine that planning level MEP right from the get-go of a project using SELDM. We did this in 3 phases. The first step was to build a version of SELDM that's specific to North Carolina. I'll go into what that means a little bit of detail in a minute. Then we used that North Carolina version of SELDM to run a bunch of our own scenarios, combinations of upstream basin characteristics, different versions of highways, and basically built this catalog, which then can be drawn from, and that's where we built our decision support tool. So I'll go into each of these 3 steps in a bit more detail here. First was building the North Carolina specific SELDM model. And if you'll remember from Greg's conversation, all these different statistics go into SELDM: storm flow rates and synthetic hydrographs, water quality constituents from upstream, the highway runoff, all these things. And we use North Carolina specific data to kind of refine those variables in our version. So there were 266 stream gauges across the state to compute our stream flow stats. 57 of those gauges also had water quality information, so we could understand correlations from upstream stream flows and the water quality that is being carried by that stream flow. We pulled data from 7 reports from the North Carolina DOT. 7 doesn't sound like a ton, but in those 7 reports there were over 25,000 samples that we added to the highway runoff database. So that's a lot of data specifically to the runoff water quality you would expect to see in North Carolina. And then additionally, 17 runoff BMP pairs were also monitored, and those data were used to define how well a BMP performs hydrologically and in terms of water quality treatment. So all of those data sets go into the already kind of pre-built SELDM version, and we refined it to the North Carolina data. And that's wonderful. As Greg showed, SELDM's pretty easy to use, but in conversations with the North Carolina DOT and our regulators, we decided, if our goal is to streamline this determination of MEP, it doesn't really make sense to try to teach hundreds, maybe, over 1,000 different hydrologic engineers or hydraulic engineers across the state how to use this model. It's not necessarily in the scope of practice to understand the statistical outputs of a stochastic model, right? So instead, we stepped in and we ran the model ourselves. Here's the schematic that Greg showed in his presentation. Again, it's a combination of first, what's coming from our upstream basin. I wonder if I can, yeah, so, are we talking about a basin that's in a really small headwater and we're crossing our river right there? Are we more on a main stem? We have a much larger upstream basin. Are we in a forest or maybe somewhere that's more developed or an ag or something like that? All these different combinations are important to understand. We randomly sampled 1,000 stream crossings that actually exist in North Carolina and developed distributions of what we expect to find across our state in terms of expected upstream basin characteristics. And then you also add in the highway runoff water and concentrations. So you see, are we building a small 2-lane highway? Do we have a 6-lane road with a center median and lots of large shoulders? Are we talking about a long, skinny road that's going to take a long time for the water to get to the stream, or a shorter road with a quicker lag time? All those combinations were inserted as well. So in combination of all those basins and highway characteristics, we ran that many, what was that, 112,320 scenarios in our North Carolina SELDM model. And again, each of those scenarios is simulating 30 years of runoff data. So that's, take that number times 1,500 or more runoff events, and that's the amount of events that we basically simulated in SELDM. These aren't really important, but this just shows the combinations of different characteristics we tested. So drainage basin sizes ranging from 0.1 square miles, a really small basin, all the way up to 500 square miles, just to understand that range of outcomes. And here's all the others that we tested. The bottom left, there's 3 different ecoregions in North Carolina. Greg was mentioning some of those in the New England as well. In North Carolina, we've got the Blue Ridge, which is the mountains, the Piedmont, which is kind of central North Carolina, and the coastal plain. And all those have different soil characteristics and slope relationships. So you basically can run the model in any of those regions, and it's going to give you more specialized results for that area. Again, the combination of roadway characteristics are shown. The only one to point out really is this BMP type in the bottom right. The 3 types are basically status quo, no BMP. The basic BMP, or what North Carolina calls minimum measures, is that vegetated conveyance, a grassy swale. And then advanced BMP is, they refer to that as kind of a suite of BMPs in their toolbox. That would include a bioretention cell or a more advanced bioretention swale, something along those lines. So now we've ran all those simulations, what are we going to do with them? And that's where comes in this decision support tool that we built. And again, this is in cooperation with the folks at DOT and also the regulators. We're all basically in the room as we made some of these decisions on how to build this decision support tool. And I'm going to do something risky, which is exit out of PowerPoint and try to show you a demonstration of the tool. So everyone cross your fingers. Oh boy, I don't know what that means. All right, so this is the tool. I hope the folks in the back can see it. Can you read that, or should I zoom in? I got a thumbs up, so I think we're good. Okay. The front page just shows some of our background, but I'm going to skip over that. There's also an instruction sheet, and really the meat and potatoes is here in our input slide. So the hydraulic engineer just puts in their project name. We'd say our site description. We're in the crystal room, and it's me. Oops. Who's running this analysis, right? And then the first set of tabs in this box are the different values you pull from stream stats. So these all describe the upstream basic characteristics that Greg was showing. You can see here here's the shorthand name for some of these, but they're basically channel slope in your upstream basin is the top one, drainage area in square miles. This is the most recent imperviousness values we have available in the North Carolina stream stats application. And then these bottom 4 just determine which of those ecoregions we're in between Blue Ridge, Piedmont, and Coastal Plain. I actually have these values in an example tab in the back. So I'm just going to borrow the actual numbers. This is what the report for a stream stats output would look like. You can see your basin. For this example, it's a pretty small basin in a relatively highly developed area. You can see it's a slope of about 100 feet per mile, drainage area of 0.61 square miles, 39% impervious, and we're all 100% in the Piedmont. So I'm just going to copy these numbers in here. They're all right here. And the hydraulic engineer would basically just copy those numbers from their stream stats report right into the table. Next, the bottom three, as you can see, these are the highway drainage characteristics that we mentioned. So again, we're looking at three main characteristics here. The impervious area, which is basically the full pavement that would be draining to a receiving water body. The average highway slope, so that's again just in percentage in this case, so feet per feet. And longest drainage length is basically if you're pulling in water from two sides of an approach, which is the longer of the two sides. Again, I've got a worked example in this back sheet. And this is, again, preliminary stages. So I've just highlighted the highway, used a topo map to figure out kind of the drainage divides, marked them here with some triangles, and here's our crossing in this red. Different drainage length on either side. We would pick the longest, so 1100. I calculated the average slope for each of these two, and then also the drain, or the area that drains to the highway. I'm just going to, again, copy these right from my example. It's a 2.8 acre highway that's draining down. The percent slope in the approaches was about 6%, and our longest drainage length was 1,100 feet. These three numbers go into our tool, and then you just scroll down to the bottom, and the output is automatically generated. In this case, the recommended preliminary treatment goal would be minimum measures. That's maybe some North Carolina lingo, but that basically equivalates to vegetated conveyance. Just to check our logic here, let's assume we have a much larger highway, which would be more impactful. I'm just going to change that to 20 acres, and you see that the output is automatically changed to show that we need a BMP from their BMP toolbox. If we were to go in the other direction, that would show us that direct discharge might be acceptable at this location if it was a really small highway draining into that stream. Just to cover my bases here, this is all part of that data-driven approach. In the actual North Carolina permitting kind of recommendations, they would never actually propose a direct discharge. I think their minimum is always minimum measures. But it's good to have that background to show that in this scenario, direct discharge would probably not affect the stream too much. That's all there really is to show on the design tool. The user would then just go to the summary report, automatically fills in all their project information, gives us a timestamp if we do have iterations of this throughout the preliminary design and planning stage, if there's different changes, and it spits out their recommendation here. If I were to go and do like a print preview, it just all fits neatly on one page, and this can be submitted to the regulator. And this basically is where the discussion starts in determining that MEP. So instead of starting with a blank slate, we now have a starting point that serves as the foundation for those discussions, derived from data specific to North Carolina. All right, so I'm gonna go back in here. And in the background of that tool, we made it as user-friendly as possible, but in the background there's a lot of stuff happening. As I mentioned before, there's a whole catalog of different scenarios we ran from. The Excel tool is basically stating in the first step, as you input those highway characteristics and the basin characteristics, which of those 100,000 plus scenarios is most closely aligned with my specific project inputs, and then it pulls the summary statistics from that single scenario. So again, there's 1,500 simulated storms from that event. And then we ask our first question kind of in this decision train. Does the untreated runoff increase this statistic we call QW10 by 25% or more? Greg alluded to this 25% in his presentation. Basically, it's a rough uncertainty bound for any sort of water quality measurement you're taking in a stream. So we use that as kind of our starting point threshold. And the QW10 refers to how many of those 1,500 events exceeded a water quality change of 25%. So if 10% of our storms had a water quality change downstream of greater than 25%, we would say that the answer would be yes, and we would go on to the next level of treatment. If it was less than 10% of storms had that insignificant change to downstream water quality, we'd say no, and direct discharge might be okay. Instead, if more than 10% of those events had a downstream increase, we would say yes and follow this arrow. We'd basically ask that same question. Instead of untreated water quality changing downstream, we would look at the vegetated conveyance, water treated by that, the grassy swale and potential infiltration that would occur along the way. If we are not exceeding that 10% of events beyond the 25% increase threshold, we would say that minimum measures are acceptable. And if they are not acceptable, then that's when we go into that BMP toolbox, so the more advanced. I don't want to emphasize that QW10 statistic. It gets a little bit convoluted, but basically this is a statistic and decision matrix we developed in cooperation with the regulator, and they agreed to it as a good way to determine the MEP standard. So that's about it. The tool is officially in use. It's been for the past not quite a year, but we've heard some good feedback. The hydraulic engineers and regulators are a fan of how it's been working so far, and it really has started to streamline those conversations. And I'd like to thank our partners at the North Carolina DOT. That's Andy McDaniel, Brian Lipscomb, and Ryan Mullins. They helped out a lot. My co-authors, Curtis and Greg, of course, was there to help us out along the way. Thank you very much for your time, and do we have time for questions? Okay. Sure. Okay. Yeah, sure. So this tool, basically, it does have to make some assumptions about the upstream. We do not have ways to kind of adjust. I mean, you could go in and use a manual SELDM run. So like instead of pulling from the catalog, you could probably change the upstream statistics for the water quality and run SELDM, kind of like how Greg was talking about. You can use SELDM on a case-by-case basis if you want. And we actually have had discussions, not exactly that scenario, but other ones, for example, if our crossing was just below like a dam, for instance, that's not going to be your expected stream flow statistics. Or if we're maybe at the coast and it's a tidal scenario. So I think we're in talks with the DOT to kind of figure out when is this tool most applicable, when can we then use the catalog, or when would we want to suggest a more specific SELDM run that probably DOT runs themselves, where they would maybe tinker with those input statistics. So maybe changing that water quality upstream and then rerunning kind of a solo simulation for that specific project. Anything I should add there, Greg, or is that? Okay. Any other questions? All right, so yeah, I'll be here through tomorrow. If you have any questions, come find me. Thank you.